NENOMATICA, where mathematics meets YouTube excellence. Welcome to this lesson on exponent properties. Today we're going to explore an important exponent rule, raising a power to another power. When we have a power raised to another power, there's a special rule we can follow to simplify the expression. Let's first state the rule formally. For any real number, a, and integers m and n, when we raise a to the power of m, and then raise that result to the power of n, this equals a raise to the product of m times n. Let's understand this with a simple example. Consider the expression 2 cubed to the power of 2. First, we evaluate what's inside the parentheses. 2 cubed equals 8. Then, we raise 8 to the power of 2, which gives us 64. But according to our power-to-power rule, we can also calculate this by multiplying the exponents. 3 times 2 equals 6. So 2 raised to the power of 6 also equals 64. Let's verify. 2 to the power of 6 is 2 times 2 times 2 times 2 times 2 times 2, which equals 64. This confirms that both methods give us the same result. Let's visualize this rule. When we raise a to the power of m, we're multiplying a by itself m times. Then, when we raise this result to the power of n, we're taking that entire product and repeating it n times. This is equivalent to multiplying a by itself m times n times, which is the same as multiplying a by itself m times n times. Now, let's go through a formal proof of this property. We want to prove that for any real number a and integers m and n, the expression a to the power m raised to the power n equals a to the power m times n. Let's start with the left-hand side. A to the power m raised to the power n. By the definition of exponents, this is a to the power m multiplied by itself n times. So we get a to the power m times a to the power m, and so on, n times. Using the rule for multiplying powers with the same base, we add the exponents. So we have a to the power m, and so on, with m appearing n times. This simplifies to a to the power m times n. And that's our proof. Let's start by looking at our first example. What happens when we have a power raised to another power? Let's find out. Let's think about what this means. We have 5 cubed, and then this entire expression is squared. We can expand this to see that it's 5 cubed times 5 cubed. When we multiply powers with the same base, we add the exponents. So this becomes 5 raised to the power of 3 plus 3, which is 5 to the power of 6. But there's actually a simpler way to think about this. When we raise a power to another power, we can multiply the exponents. So 5 cubed raised to the power of 2 equals 5 to the power of 3 times 2, which is 5 to the power of 6. Now, let's look at another example. Here, we have 14 to the power of 9, and this entire expression is raised to the power of 4. Using the same rule, we can expand this to see that it's 14 to the power of 9 multiplied by itself 4 times. Adding the exponents, we get 14 to the power of 9 plus 9 plus 9 plus 9, which equals 14 to the power of 36. But again, we can apply our power of a power rule to directly multiply the exponents. 14 to the power of 9 raised to the power of 4 equals 14 to the power of 9 times 4, which is 14 to the power of 36. Now, let's look at a practice exercise. Using what we've learned, let's evaluate the expression 2 cubed raised to the power of 4. We can apply our power of a power rule directly. 2 cubed raised to the power of 4 equals 2 to the power of 3 times 4. Calculating 3 times 4, we get 2 to the power of 12. Alternatively, we could expand the expression to get 2 cubed multiplied by itself 4 times. Adding the exponents, we get 2 to the power of 3 plus 3 plus 3 plus 3, which is 2 to the power of 12. Let's try another exercise. This time, we have a variable expression, a to the power of 4 raised to the power of 3. Applying our rule, a to the power of 4 raised to the power of 3 equals a to the power of 4 times 3. Computing 4 times 3, we get a to the power of 12. We can also expand this as a to the power of 4 multiplied by itself 3 times. Adding the exponents, we get a to the power of 4 plus 4 plus 4, which is a to the power of 12. Finally, let's examine the general case. If we have a to the power of n raised to the power of 4, what do we get? Using our power of a power rule, a to the power of n raised to the power of 4 equals a to the power of n times 4. Simplifying, this equals a to the power of 4n. Let's also show the expanded form. This would be a to the power of n multiplied by itself 4 times. Adding the exponents, we get a to the power of n plus n plus n plus n, which is a to the power of 4n. Let's summarize what we've learned. The power of a power rule states that when you have a power raised to another power, you multiply the exponents. This can be written as a to the power of m raised to the power of n equals a to the power of m times n. This rule works for any base and any exponents, making it a powerful tool for simplifying complex expressions. Today we'll focus on simplifying expressions with nested exponents, learning how to apply the power rule to transform complex expressions into simpler forms. The key rule we'll be using today is the power of a power rule. When we have an expression in the form of a power raised to another power, like a to the m, all in parentheses, raised to the n, we simplify by multiplying the exponents. So this equals a raised to the m times n. Let's look at our first example. We need to simplify the expression 2 raised to the third power, and that entire quantity raised to the fourth power. Applying the power of a power rule, we multiply the exponents. 3 times 4 equals 12. So our final result is 2 raised to the 12th power. Let's try another example. Here we have 2.5 squared, and that entire quantity is cubed. Again, we apply the power of a power rule. We multiply the exponents. 2 times 3 equals 6. So our result is 2.5 raised to the 6th power. Let's look at one more example that combines multiple rules. Here we have the fraction 2/3 squared, and that entire quantity is raised to the 0 power. First, let's apply the power of a power rule. We multiply the exponents. 2 times 0 equals 0. Now, we need to remember another important rule. Any number raised to the 0 power equals 1. So our final result is simply 1. In this video, we'll work through several examples where we apply the rules of exponents to simplify complex expressions to their numerical value. Let's start with our first example, 25 raised to the power of 5. To simplify this expression, we can rewrite 25 as 5 squared. This allows us to apply the power of a power rule, which states that when we raise a power to another power, we multiply the exponents. We now have 5 squared, raised to the power of 5. Using the power of a power rule, we multiply the exponents. 2 times 5 equals 10. Therefore, 25 to the power of 5 equals 5 to the power of 10. Let's move on to our second example. We have the expression 2 cubed times 3 squared, and this entire product is raised to the power of 3. For this example, we need to apply the power of a product rule. Which states that when a product is raised to a power, we can distribute the exponent to each factor. Now we have 2 to the power of 3, raised to the power of 3, multiplied by 3 to the power of 2, raised to the power of 3. Next, we apply the power of a power rule we just learned. For the first term, we multiply 3 times 3, which equals 9. For the second term, we multiply 2 times 3, which equals 6. Therefore, our final answer is 2 to the power of 9 multiplied by 3 to the power of 6. Now, let's tackle the third example. We have a to the power of 3 raised to the power of 4, multiplied by b to the power of 4 raised to the power of 3. For this example, we'll first apply the power of a power rule to both terms. For the term with variable a, we multiply 3 by 4 to get 12. For the term with variable b, we multiply 4 by 3, which also equals 12. Now we have a to the power of 12 multiplied by b to the power of 12. Since the exponents are the same, we can use the product rule to write this as a times b raised to the power of 12. Therefore, our final answer is a times b all raised to the power of 12. Let's summarize what we learned in this lesson. We use the power of a power rule to multiply exponents when a power is raised to another power. We applied the power of a product rule to distribute an exponent over a product, and we combined powers with the same base using the product of powers rule. Practice these rules to simplify, where we'll learn about the properties of exponents and how to use them to simplify complex expressions. In this lesson, we'll focus on 4 important properties of exponents. First, the product of powers with the same base. Second, the power of a power. Third, the power of a product. And fourth, the quotient of powers with the same base. Understanding these properties will help us simplify complex expressions efficiently. Let's look at our first example. We need to simplify the expression a squared cubed times a cubed to the 4th power times b cubed squared times b to the 4th cubed. Let's analyze this step by step. First, let's apply the power of a power property, which states that when we have a power raised to another power, we multiply the exponents. Let's apply this to each term. For a squared cubed, we multiply 2 by 3 to get a to the 6th. For a cubed to the 4th, we multiply 3 by 4 to get a to the 12th. For b cubed squared, we multiply 3 by 2 to get b to the 6th. And for b to the 4th cubed, we multiply 4 by 3 to get b to the 12th. Now let's simplify by calculating the exponents. Next, we'll use the product of powers property, which states that when we multiply powers with the same base, we add the exponents. Let's apply this to our expression. For the terms, we add 6 and 12 to get a to the 18th. For the b terms, we add 6 and 12 to get b to the 18th. Now, we can use the power of a product property to rewrite this expression. We can rewrite our expression as a times b raised to the 18th power. So our final answer is a times b to the 18th power. Let's look at a second example. We need to simplify the expression 16 to the 7th power times 8 to the 5th power. Let's tackle this step by step. First, we'll express 16 and 8 in terms of powers of 2. 16 and 8 in terms of powers of 2. We know that 16 equals 2 to the 4th power, and 8 equals 2 to the 3rd power. Now, we'll use the power of a power property again to simplify. For 2 to the 4th to the 7th power, we multiply 4 by 7 to get 2 to the 28th power. For 2 to the 3rd to the 5th power, we multiply 3 by 5 to get 2 to the 15th power. Now, we'll use the product of powers property to combine the exponents. We add the exponents 28 plus 15 to get 2 to the 43rd power. So our final answer is 2 to the 43rd power. For our third example, let's simplify 25 to the 11th power divided by 125 squared. As before, we'll tackle this step by step. First, let's express both 25 and 125 as powers of 5. We know that 25 equals 5 squared and 125. We know that 25 equals 5 squared and 125 equals 5 cubed. Now, we'll use the power of a power property. For 5 squared to the 11th power, we multiply 2 by 11 to get 5 to the 22nd power. For 5 cubed squared, we multiply 3 by 2 to get 5 to the 6th power. Now, we'll use the quotient of powers property, which states that when we divide powers with the same base, we subtract the exponents. With the same base. Let's look at our first example. We need to write the following expression as a single power with a numerical base. To simplify this expression, we'll first convert everything to powers of the same base. Looking at the different terms, we can see that 27, 9, 81, and 3 are all powers of 3. 27 equals 3 cubed, 9 equals 3 squared, 81 equals 3 to the 4th power, and 3 is already in the right form. Now we'll apply the power of a power rule, which states that when a power is raised to another power, we multiply the exponents. 3 cubed squared becomes 3 to the 6. 3 squared to the 5th power becomes 3 to the 10. And 3 to the 4th power cubed becomes 3 to the 12th. Next, we'll apply the product of powers rule to the numerator and denominator separately. This rule states that when multiplying powers with the same base, we add the exponents. In the numerator, we add 6 plus 10 to get 3 to the 16th. In the denominator, we add 12 plus 2 to get 3 to the 14th. Finally, we'll use the quotient of powers rule. This rule states that when dividing powers with the same base, we subtract the exponents. So, 3 to the 16th divided by 3 to the 14th equals 3 to the power of 16 minus 14, which is 3 squared. Let's move on to our second example. This time we need to simplify 5 to the 12th power times 2 to the 18th power as a single power. For this problem, we need a slightly different approach. we can't express the numbers as powers of the same base easily, so instead we'll rewrite the expression to get the same exponents for both terms. We can rewrite 5 to the 12th as 5 squared to the 6th power, since 5 squared is 25, and 6 times 2 equals 12. Similarly, we can rewrite 2 to the 18th as 2 cubed to the 6th power, since 2 cubed is 8, and 6 times 3 equals 18. Now, we apply the power of a power rule to evaluate the powers. 5 squared to the 6th power equals 25 to the 6th power. 2 cubed to the 6th power equals 8 to the 6th power. Notice that now both terms have the same exponent, 6. When multiplying terms with the same exponent, we can use the product of powers rule in a different way. A to the m times b to the m equals the product of a times b, all raised to the power of m. So we get 25 times 8, all raised to the 6th power. 25 times 8 is 200, so our final answer is 200 to the 6th power. Let's try one more example. This time we need to simplify 2 to the 22nd power times 3 to the 33rd power. We'll use the same strategy as in the previous example. First, we'll rewrite the expression to get the same exponents. We can rewrite 2 to the 22nd as 2 squared to the 11th power, and we can rewrite 3 to the 33rd as 3 cubed to the 11th power. Now we apply the power of a power rule. 2 squared to the 11th power is 4 to the 11th. 3 cubed to the 11th power is 27 to the 11th. Since both terms have the same exponent, we can use the product of powers rule. We multiply the bases 4 and 27, and keep the exponent 11. 4 times 27 equals 108. So our final answer is 108 to the 11th power. We need to simplify the expression 1/2 to the power of 7 times 2 to the power of 20 divided by 4 cubed times 8 squared. Let's begin by focusing on the numerator and denominator separately. In the numerator, we have 1/2 to the power of 7 times 2 to the power of 20. In the denominator, we have 4 cubed times 8 squared. Now let's rewrite all terms as powers of 2. First, 1/2 to the 7th power is 1 over 2 to the 7th power. 4 is 2 squared, and 8 is 2 cubed. Let's continue simplifying. We can rewrite 1 to the 7th power as simply 1, since any power of 1 equals 1. Now that everything is in terms of powers of 2, we can use the power rule to simplify the denominator. Now, we can multiply the exponents in the denominator. 2 to the 6th power times 2 to the 6th power equals 2 to the 12th power. So we have 2 to the 7th power times 2 to the 12th power, which equals 2 to the 19th power in the denominator. Finally, when dividing expressions with the same base, we subtract the exponents. So 2 to the power of 20 divided by 2 to the power of 19 equals 2 to the power of 20 minus 19, which equals 2 to the power of 1, or simply 2. Let's move on to our second example. Here, we need to simplify the expression 2/5 to the power of 7 times 4 25ths to the power of 4, divided by the product of 8 over 125 to the power of 2 and 4/10 to the power of 4. Let's start by rewriting some of these fractions in a simpler form. 4 over 25 is actually equal to 2/5 squared. We can verify this. 2/5 squared would be 4 over 25, which matches our fraction. Similarly, let's check what 8 over 125 is in terms of 2/5. We can write it as 2/5 cubed, and 4/10 simplifies to 2/5. Now, let's use the power of a power rule to simplify further. When we raise a power to another power, we multiply the exponents. So 2/5 squared to the power of 4 becomes 2/5 to the power of 8, and 2/5 cubed to the power of 2 becomes 2/5 to the power of 6. Now we can combine the powers in the numerator and denominator using the product of powers rule. In the numerator, we get 2/5 to the power of 15, since 7 plus 8 is 15. In the denominator, we get 2/5 to the power of 10, since 6 plus 4 is 10. Finally, we can apply the division of powers rule. When dividing powers with the same base, we subtract the exponents. So 2/5 to the power of 15 divided by 2/5 to the power of 10 equals 2/5 to the power of 5. Let's summarize what we've learned about simplifying expressions with exponents. We use several key exponent rules. First, we use the product of powers rule, which states that when multiplying with the same base, we add the exponents. Second, we use the power of a power rule, which states that when raising a power to another power, we multiply the exponents. Third, we use the division of powers rule, where we subtract exponents when dividing expressions with the same base. And finally, we learn to rewrite expressions in terms of a common base or fraction to make simplification easier. Try these techniques on similar problems to strengthen your understanding of exponent rules. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.